We are now talking about subspaces of Rn of class finding solutions of systems of equations. And then we spent the next section, section 1.3, investigating properties of those solution sets. And we're going to keep doing that. We haven't done that completely, but at least we got a good start in section 1.3. So we've kind of started this. Today we're going to continue this, and we're going to talk about a few important ideas. The idea of a subspace of a vector space, and we're going to talk about a term called span and what that means. And then we're going to look closely at a homogeneous system, which are a little bit special and have some unique traits. So let's think about, for example, think about all of the vector space R4. These are all the vectors in the world that have 4 elements of any real numbers. So there's an infinite number. There's tons of them out there. And within this set, R4, there's little subsets. Like we could think of one particular subset would be, like think about the 2-element subset 1, 1, 1, 1. That's definitely sitting in there. And here's another vector that's definitely sitting in here. And if we just had a subset, a 2-element subset of those 2 vectors, so this is a 2-element subset of R4. But there's tons of other subsets. Another subset I want to look at and think about is, what about the subset of all the vectors that start with a real number, but then the other 3 entries are all 0? So an example of something that would be in here is like 5, 0, 0, 0, and 2, 0, 0, 0 is in here. And any real number, we'll call it A, 0, 0, 0, is sitting inside this subset. And we'll draw these little dots because there's an infinite number of them. They're all over the place. Okay, so this is an infinite subset. And what happens if you add this second subset here? What happens if you add 2 vectors that are in that set? Do you could the solution ever pop out and be something that doesn't already belong in here? In other words, a question that we can ask is this set, this little subset, this little infinite subset, is this closed under vector addition and scalar multiplication? So think about that for a minute. Could you ever take a linear combination of 2 vectors in there and pop outside the set? Let's see, let's think about this. Well, what if we took 5, 0, 0 plus 2, 0, 0, 0? We'd get 7, 0, 0, 0, which is already in the set. It's not written, but it's in here. What if you took like 4 times this vector? You'd get 20, 0, 0, 0, and that is of this form, so it's already in here. In fact, any linear combination of these, the last 3 elements will definitely still say zeros, and the top elements will be some real number. So the answer to this question, is it closed under vector addition and scalar multiplication? Yes, absolutely. You'll never be able to pop out of that set. And when something is closed under vector addition and scalar multiplication, we call it a vector space. And so this is, it's a vector space, but it's also a subspace, because it's a vector space sitting inside another vector space. So this is a subset. In contrast, let's think about this little 2-element set. What if I add this vector to this vector? 1, 1, 1, 1 plus 2, 2, 2, 2. Then I get something that's actually outside of the set. I would get 3, 3, 3, 3, which is not part of this subset. So this guy here, it's a subset, but it's not a subspace because it's not closed under vector addition. So these are big ideas, and we'll hit them kind of again and again. But we want to kind of ingrain in our brains what it means to be a vector space or a vector subspace. And a vector space, since we're talking about just the spaces Rn, we'll talk about other ones later, much later in the course. But for our purposes right now, a vector space, all that it has to do to qualify as a vector space, there's only 2 qualifications. It has to be closed under vector addition and scalar multiplication. If you do either of those to 2 vectors, 2 or more vectors, you better get something that's already in the set. So from this big picture, we see that within a vector space, you'll have some subsets which aren't a subspace or a vector space in their own right, and you'll have some subsets that are also a vector space, so they become a subspace of the larger vector space. We just saw that for a subset to be a subspace, these 2 conditions have to be met. So for the rest of this section, we're just going to look at 4 examples, and we're going to learn a new skill. We're going to learn to prove something is a subspace. So let's start with our first example. And right off the bat, we're going to prove something is a subspace. So we'll say let W be the subset of R3 of all vectors of the form A, B, B. So you could think about what those would look like. Pretty much any 3-element vector where you have a first element and then the second and third elements are the same thing. It can be different from the first element, but the second and third element have to be the same thing. So first off, our first job is to give some specific vectors in W. And is there a finite number or an infinite number of vectors in W? Definitely infinite. An example of a vector in W would be 1, 2, 2. I guess I just wrote it as a column vector. Let's write it as they've written it. So 1, 2, 2 is in W. 3, 4, 4. Just any real number. It could be 0.5 and 1/7, 1/7. Just the second and third elements have to be the same number, and that's the only qualification. Okay. The second thing we're asked to do is the big thing. Show that W is a subspace of R3. It's definitely a subset because it's sitting inside of R3. But to show that it's a subspace, we have to prove that it's closed under vector addition and scalar multiplication. So these types of vectors. And we can't just prove it for one specific or 2 specific vectors. We have to prove it in a general way. So we need 2 arbitrary vectors in W for this proof. So we need 2 arbitrary vectors in W. And so one way to do this is to say, okay, here's a vector U, and we can't give it specific numbers, but we can say that U is this, ABB. And then there's another vector V, which, well, we don't want to use the same letters because that would say that they're two equal vectors. So it has to be another arbitrary vector. And in this case, we'll say, okay, V is CDD. Follows the pattern. It just happens to be some two other arbitrary numbers. So our first job is we're going to show that it's closed. W is closed under vector addition. So let's take U plus V, and we'll add them together. Okay, if we add these together, that means we're adding A plus C, and that would be, that's the first element of this new vector. And then the second element would be B plus D, and the third element would be B plus D. This is what we get when we add up our two arbitrary vectors. And so we ask, the big question is this new vector, this is our question, is it an element of W? So this symbol right here just means element of. And we're asking this question, does this belong in the set of vectors that look like this? Well, this set is basically just take any first element, and your only qualification is the second and third elements have to match. Okay, we have any first element, and do our second and third elements match? Yeah, they do. Okay, so yeah, it actually is an element of W. Okay, so it passes the test for vector addition. It's closed under vector addition. You add any two arbitrary vectors, and you'll get another vector that's sitting inside W. The next job is to show it's closed under scalar multiplication. So we say, okay, we need a scalar. We don't want to use C because it's being used somewhere else in vector V. So we'll say, let K be a scalar, just some real number. Then we can look at scalar multiplication, like K times the arbitrary vector U. And in this case, that'll be K times A, K times B, K times B. And so our question there is, question mark, is this an element of W? In other words, and remembering that W is, just as it always has been, the first element and then the second and third elements have to be identical. That's the only condition on being in W. And so we have a first element, can be anything, and are the second and third elements identical? Yes, they are. So we can say that that scalar multiple is in W. And so now we know that W is closed under both addition and vector addition and scalar multiplication. So therefore, those are the only two things we had to prove. W is a subspace. And that's what a proof where you're trying to show that something is a subspace can go. What we saw in the last example is you can't just prove something is true by one particular case. So in math, you can't prove something is true just by showing one specific example. You really have to show that it's true in a general way. And so that's why we were using such arbitrary vectors and not particular numbers. But sometimes it can be helpful to look at a particular number example just to understand better what's going on. So this is not part of the proof. But we're going to look at some numbers just to clarify in our own brains what's happening. So let's take two random vectors in W, like 2, 3, 3 plus 5, 7, 7. Both of those are vectors in W, and if you add them together, you get 7, 10, 10. And yeah, that's back in W because you have the second and third elements are the exact same number. Let's try something with scalar multiplication. 3 times the vector 2, 3, 3. This will be a scalar multiple of something in W, and that equals, let's see, that's 6, 9, 9, which is also another element in W. So it's like you're not going to be able to get out of W by taking any linear combination of two vectors that are already in there. And that makes a subspace. On the other hand, if you want to prove something, you want to disprove something, or prove something is false, a claim is false, it's okay just to use a specific example because one time of it failing and it's false. So in math, you can prove something is false by showing just one time that it fails. And a little later on we'll look at an example of this. But so that's an important. Those two notes are a good, an important statement about going about proofs. Okay, the last thing that we're asked to do in this problem, the final thing, is they're going to ask us to give a geometrical interpretation of this subspace. We're still in R3, so we could still visualize this with our brains. If we were in R4, that'd be way harder, and they probably wouldn't ask the question, but we're in R3, so give a geometrical interpretation of this subspace. Okay, this subspace where the first element can be anything and the second and third elements are the same thing. So vectors that look like A, B, B, you could rewrite this as A1, 0, 0 plus B0, 1, 1. So basically, this space is really like a scalar multiple of this vector 1, 0, 0 plus a scalar multiple of this vector 0, 1, 1. And so I want to think about what those two vectors look like. And say that this right here is, this axis is x1, this will be our x2, and up here is x3. So we're in three-dimensional space, and so that first vector 1, 0, 0 is just one unit on x1 and no units on x2 and x3. And the second vector 0, 1, 1 is 1 unit on x2, 1 unit on x3, so it looks something like this. So you may be able to kind of visualize that if we took any linear combination of these two, you you know, if we stretched them out and added, we're going to get basically a two-dimensional plane constructed by the those two vectors and their linear combinations. So that subspace W is actually a plane sitting inside 3 space. So W is a plane. And any linear combination of these guys is not going to escape the plane. It's going to stay in the plane created by those two. It reminds me, the very first original Superman movie, at the very beginning of the movie, there's these, I can't even remember why it's important to the story, but there's these 3 like people that are in front of the tribunal, and they get banished to, I don't know, they're indicted on something or they're convicted, and they get trapped in this two-dimensional plane and they can't get out. They're these 3 people. And I think about that when I think about this subspace, because these vectors, you try to take any linear combination of them, and this space, they can't escape out of it. So I found a picture of what I was talking about, that old Superman movie. They're here on the planet Krypton, and these 3 criminals get trapped in this plane, and that's like their jail cell. But that's kind of how this subspace is. Once you get in that plane, in this 3-dimensional space, there's no getting out of it for the set W. Okay, so kind of to summarize what we just learned, any vector in W, still on example 1, any vector in W can be written as, of course, ABB. That was how it was introduced, but can also be written as a linear combination. That phrase is going to come up again and again, of those 2 important vectors that we just saw, 1, 0, 0, and 0, 1, 1. So for example, take some arbitrary element of W, like 599. This is equal to 5 times 1, 0, 0 plus 9 times, whoops, 0, 1, 1. So from those 2 vectors, these are important vectors in the world of the subspace of W, because from those 2 vectors you could generate any other vector in W, and that's an important. So those are 2 sort of critical vectors. They may not be the only ones, and they're not the only ones that could act as generators. But when we find these vectors that can generate the whole space, we say that 1, 0, 0 and 0, 1, 1 span, span the set W, because any vector in W can be generated by those 2. This is one of our sort of keywords for this section, this idea of spanning. We'll see, this will come up again, but we've seen it for the first time here. Oh, and I definitely need to put a little teeny tiny, it's not very good, comma there. Okay, let's move on to a different example. Another subset of R3. And This time, we're going to say, let W be a subset of R3. Consisting of vectors of the form A plus 2, B. So all the vectors in W have to follow this pattern, and then the question is W a subspace of R3? And the only thing we have to do is check vector addition, if it's closed under vector addition and scalar multiplication. So we know that W is a subset of R3 for sure, because it's a set sitting inside R3, but is W a subspace? That's the question we're going to answer. And so we start how we started before. We're going to look at vector addition and see if it's closed under vector addition. So here we'll let U equal A plus 2B, and we're going to take another arbitrary vector V, and we're going to let that equal C plus 2D. We just needed different numbers because they're different arbitrary vectors. And now we're going to look at U plus V. Hopefully if it's the subspace, it should still be in W. This will be, let's see, the first elements, we add them together, A plus C. The second elements, we have A plus 2 and C plus 2. Adding those together, we get A plus C plus 4. And the last elements should be B plus D when we add them together. Okay, this set has the pattern where we have a first element, and then the second element is 2 more than the first element. And then the third element is just anything, some arbitrary other thing. So we have a first element, and we need here to have the second element be 2 greater than this, but we have a problem, it's 4 greater. And so that just disqualified it. So we're not in W anymore. When we added these two vectors up, somehow we got out of W. So these two vectors escaped the, that glass prison two-dimensional thing. But so we know that we can say, wait, this is not in W. And so this right here is going to prove that W is not a subspace. So therefore, W is not a subspace. It's not closed under vector addition. Okay, so example 1 was something that was a subspace. Example 2 is something that isn't a subspace. So we can stop the proof right here. We don't even have to look at scalar multiplication, because if it fails this, then it's not a subspace. Okay, for our third example, we're going to have a little bit of a flashback to our unit in 1.2. Say that we had a solution set of a system of equations, and they looked something like this. So this is something that definitely could have been generated by a system of equations. And we want to answer the question, is it a subspace? So we can see the ideas from the first 2 days where we were solving equations coming around, and now we're looking at the solutions to those systems and deciding if it's a subspace. So this one, I have a hunch because of example 2. Example 2 failed, and this one is looking kind of similar. So I have a hunch that it's going to fail as a subspace. So I'm going to prove it or disprove it. I'm going to prove that it's not a subspace in a really easy way by just showing that it fails right off the bat. So let's see, let's let r equals 0, and so that would generate the vector 2, 0, 0. If we said that r was equal to 1, just from this pattern, we would get the vector 3, 3, 1. And then I'm just going to add these two vectors together and see if it's a vector that follows that pattern. And when we add them together, we get the vector 5, 3, 1. Does this follow the pattern of the original solution set? If it does, the third element is r, so that would be 1, and the first element needs to be 2 more than that. So this would have to be, that first element would have to be 3. This is not in the solution set, so not in the set of solutions. Oh no. So because 5, 3, 1 is not in the solutions, the set of solutions, this set is not closed under addition, under vector addition. And so it's not a subspace. Okay. So before we move on to our last example, so far what we have is example 1 was a proof of something that was a subspace. Example 2, we were trying to see if something was a subspace, and it turned out that it wasn't. Example 3 was a set of solutions to a system of equations, and we were asking, is that a subspace? And it turned out to be not a subspace. We're ready for our fourth and last example of this section, and we want to pay special attention to what's going on here and even reflect back on it, because there's some deep ideas here. So this system of equations, we're going to look at the solution set to this system of equations. But before we do that, we want to think this is a special system, and there's a name for this kind of system. It's called a homogeneous system, because all of the constants are 0. So we want to remember to be looking out for that. And I'm even going to give you the solution to this system. Typically in a system of equations, we either have one, many, or no solutions. This one has many solutions, and they're all of the form 3r plus s. This is in R4, so we should expect 4 entries, minus r minus 4s, rs. This is what all of the solutions will follow this pattern. And our first job, the first thing they ask us to do is not too bad. They say find 2 specific solutions. And so we just have to decide on an R and S and plug it into the pattern for the solutions, and it'll pop right out. So we can pick any random R and S. And we'll pick some kind of easy ones. Let's say R equals 1, S equals 0, and that would generate the point 3, negative 1, 1, 0. And then let's say what happens if r equals 1 and s equals 1, and that would generate the point 4. Negative 1 minus 4 is negative 5, and then 1, 1. Okay, so we have these two. Let's just double check and make sure they are solutions. So I'm going to take this guy and think of plugging him back into these equations. So that would be 3 minus 1 is 2, minus 2 plus 0 equals 0. That one works. 6 minus 1 is 5, minus 5 times 1 is 0, plus 0 equals 0. That one works. This solution again would be 3 times 3 is 9, minus 1 is 8, minus 8 times 1 is 0, plus 0 equals 0. Okay, this is definitely a solution. We could take the time and check that one too, but I promise you it is a solution. And so the next thing, so we've done that. We've generated 2 solutions. The next thing that we're asked to do is generate a new vector from these two, from a linear combination of these two. So generate a new vector from these two in part A. From part A. Okay, well, a linear combination, if they say any new vector, I'll say, okay, let's take 2 times the first one. So 2 times 3, negative 1, 1, 0. And to that we'll add, let's say, negative 1 times the second one. The 2 and the negative 1 were arbitrary. I could have picked any numbers for those. And this becomes 6, negative 2, 2, 0, plus negative 4, 5, negative 1, negative 1. And then when I add those two together, I get 2, 3, negative 1, negative 1. Nope, sorry, 2, 3. How about positive 1 here? Yep. Okay, 2, 3, 1, negative 1. And then I ask, okay, this new thing I generated, this linear combination of those 2 solutions, does this follow the pattern of solutions? In other words, is this another solution? And so let's see here. The pattern of solutions says that I have an R and an S. Here's my R and my S. And this should be 3R plus S. So 3 times 1 plus negative 1 is 2. Okay, the first element is right. This needs to be negative R minus 4S. Is it negative 1 plus, or negative 1 minus 4 times negative 1? And that would be negative 1 plus 4, and that's 3. So yeah, it does follow the pattern. So yeah, when R equals 1 here, S equals 1, and yes, we just check that all 4 entries follow the original pattern. Okay, so in this homogeneous system, these 2 random solutions that I generated and a random linear combination of those 2 resulted in another solution. This is not a proof, but it is a point that we need to make that, let's say it like this. In a typical, oops, let's go back. In a typical system of equations, in other words, one that's not homogeneous, adding 2 solutions does not result necessarily into another solution. You don't get another solution. But in a homogeneous system, this is a very special type of system where any linear combination of 2 solutions results in another solution. And what that means is that the set of solutions to a homogeneous system is closed under vector addition and scalar multiplication. And that implies it's always a vector space. So the solution set to a homogeneous system is always a vector space. Set of solutions to a homogeneous system is always a vector space. And that is, so that's something that we're going to want to remember. Okay, some big ideas to close out this section. Let's emphasize that one. And then let's just think about what we talked about already. We talked about one of the big ideas that we saw today was proving how to we practice proving something when an Rn subset is a subspace. It's a big deal to know how to do that. And then we also, this last example brings out some special traits of homogeneous systems. And also, so that the solution set to a homogeneous system is always a subspace. And also, we want to remember the idea of span. That a set of vectors will span a space if they can generate any other vector in that space. All right, great section.